So good morning. Today we will clear the doubts in numerical problems which you asked for. The problems you mentioned was 335, then 340 and 338. So let me go to question number 335 in page number 202. So page number 202 from electric current. Current electricity. From current electricity. So question 3.35. Let me read out the question for you. The internal resistance of a galvanometer is 50 ohm. A shunt of 5 ohm is used with it. To keep the magnitude of the main current unchanged, how much resistance is to be connected with the circuit? If the main current is 1.1 ampere, then what is the potential difference across the galvanometer? When a shunt is used, when a shunt is not used. So they have given internal resistance of the galvanometer as 50 ohms. So we can take G is equal to 50 ohms. And a shunt of 5 ohms is used. So S is equal to 5 ohms. To keep the magnitude of main current unchanged, how much resistance is to be connected with the circuit? If the main current is 1.1 ampere, then what is the potential difference across the galvanometer? So they have told that the main current I is equal to 1.1 ampere. So to keep the magnitude of the main current unchanged, how much resistance is to be connected with the circuit? So this is the circuit, right? You have a galvanometer G with 50 ohms, and then there is a shunt S having 5 ohms. And it is connected to a external circuit. There will be a cell, and there is a main current of 1.1 ampere. So when you connect this galvanometer and a shunt, what happens? The main current will change because of this shunt. A current is changed. What is the difference between? Okay, what is the potential difference across the galvanometer? So you have to find the potential difference across these 2 points A and B as well, right? So this is the situation. So first of all, when you connect these two in parallel, you have 2 resistors in parallel. So let us see what is the resistance which is connected in parallel to this, and what will be the new resistance when we connect the shunt in parallel. So let me tell the shunt resistance to know that these two are in parallel. 1 by Rp will be equal to 1 by G plus 1 by S. So you have shunt resistance is equal to 50. So this is 1 by 50 plus 1 by 5. So I can, to make the denominator same, I have to multiply here and here with 10. So the result will be 10 plus 1, that is 11 by 50. Or Rp will be equal to 50 by 11. This is the parallel resistance connected to it. Now, before the main current was 1.1 ampere. Now, when you connect a new resistance, what happens? The resistance of the whole circuit would have changed. Now, the idea is to keep the circuit main current same. Okay. So, what should be the resistance connected to the circuit in order to keep the main current same? That is the question. So, we have to find. This is the effective resistance after you connected the shunt, right? So earlier the resistance was equal to G. Earlier the resistance was equal to G. So G minus R will be equal to RP. I will tell you why. Because if you connect a shunt resistance here, something in parallel, the resistance decreases, right? Of the whole circuit. So in order to increase the resistance, what should we do? When you connect the resistance in parallel, the resistance of the circuit will decrease. So in order to increase the resistance, what you should do?
Connect in series.
Yeah, we have to connect another resistance in series. So suppose what we are going to do now is we will be connecting another resistance in series. Let that be R. Okay, so in order to keep the current same, we have to increase the resistance because of the reduced current by connecting something parallel. So the total resistance will be G plus this parallel plus R. So this parallel plus R will be the total resistance now. That should be the galvanometer resistance. Before connecting the shunt, only galvanometer was there. So that should be the galvanometer resistance when you are connecting this R in series to this parallel combination. So the current will remain the same. So we have to find what is this R. So in order to get R, what you can do is R will be equal to G minus RP. You know G is equal to 50 minus 11 divided by 50. You can do this calculation by yourself. What is the answer you get by this? What will be the answer when you calculate this? You can use the calculator and find.
5.5.
Yes, 45.45. Yeah, it should be less than 50. So it will be 45.45. So that is the new resistance which you have to connect in series so that the current will remain the same. Now when you connect this new resistance of 45.45 ohms, the main current will remain the same because now the circuit will have the same resistance as when there was no shunt and no new resistance. So that is first part of the question. Then they have asked what will be the potential drop across A and B with shunt and without shunt. So first when shunt is used. So we will not consider this case. We will consider only A, B is there and the shunt is there. What should be the potential difference? What is the potential in the beginning? Did they tell the potential? Did they tell the potential? No. We know the current and we know the resistance, right? So we can tell that the potential will be equal to V is equal to current into RP because RP is the resistance when the shunt is connected. R is not there. So when the shunt is connected, the effective resistance is RP. So potential will be equal to I into RP. So I is 1.1 times, what is RP?
Teacher, Irfan is waiting.
I'm sorry, 11 by 50. It is 50 by 11. I look here. So it is RP is equal to 50 by 11. So RP is 1.1 times 50 by 11. Okay, you can do this, right?
Teacher, Irfan is waiting.
What?
Irfan is waiting.
Yeah, I just joined, I admitted him. So this will be the potential. You can do the calculation. And B, the question is what will be the potential when the shunt is not used. When the shunt is not used, there is only galvanometer here. So, and current 1.1 ampere will be flowing. So, the potential across the points will be I into G. That is 1.1 into 50. Is this clear to you? Those who asked me the doubt, is it clear to you how to solve?
Yes, teacher.
Okay, so let me cut this question and let me go to 3.38. 3.38. Okay. South, read question number 3.38, which is in page number 205.
Observe the following circuits and answer the question.
And answer the question. So I will draw the circuit. You have to read the questions. A and B, two questions are there, right? 40. It was 40, right? We are doing at 340 readings. Okay. So read the question.
Find the main current of the circuit figure 1 using Kirchhoff's law.
Okay.
That's the first question. The second one,
Mm.
if the cell AB is connected in parallel with point CD, then the rate of heat produced by the external resistance will increase or decrease. Analyze
Okay.
mathematically.
Okay, okay. So another cell is connected. AB, same EMF. Okay. So this is the circuit given, and the first question is find the main current of the circuit 1 using Kirchhoff's law. So you can directly use this equation I is equal to E divided by, there is a internal resistance and external resistance. What is the formula?
R plus small r.
R plus R. E by R plus R. Or you can also get the same equation by using Kirchhoff's formula to this loop. So starting from maybe, let me name these points as A, B, E, A, B, E, A. Okay, we are going this way. So if you are using the Kirchhoff's formula, let us start from here. Let I be the current. So I is passing through R. So I into R. When we reach here, we see the negative of the cell first. So minus 10 or minus E. And also there is a resistance 0.5 and the current flowing is I itself. So plus, we are going in the same direction of current, right? So plus I into small r. So we want to get I separate. So we can take those two terms of I together, I into R plus small r. And if I take minus R is equal to 0, minus E to the other side, it will be equal to E. So I is equal to E divided by R plus R. So either you can use this equation directly if they haven't mentioned using Kirchhoff's law. But in the question, they have particularly mentioned using Kirchhoff's law. So you will have to use the Kirchhoff's voltage rule in this loop and come up to this formula. Now you can directly apply. So E is equal to 10 divided by 10 plus 0.5. Okay, so 10 by 10.5. What is the value? 10 by 10.5?
195.
0.95 ampere. Is this part clear to you?
Yes, teacher.
Now, if a cell AB is connected in parallel, so this is the cell AB. if the cell AB is connected in parallel with the points C, D. So they have marked the points C here and D here. So parallelly, one other cell is connected. Then the rate of heat produced by the external resistance will increase or decrease. So we have to analyze two cases. What is meant by rate of heat produced? Oh, heat is a form of energy. What is meant by rate of energy?
Per time, per second, I guess.
Energy per time. What is energy per time? Energy divided by time will give you
Power.
power. So when they tell rate of energy, they mean power. So energy per time means power. So we have to find power in two cases. One is the circuit without connecting AB parallel to CD. So this is the first case we will consider for this circuit. So for this circuit, what will be the power? Power we know is equal to, how will we calculate power?
W by T.
Work. What?
Work per time.
Heat produced by time, right? What is the heat produced? H is equal to, when current I is flowing through a resistance R, what will be the heat produced? H is equal to, you have learned Joule's heating effect.
I square R T.
I square RT. So power is equal to H by T, right? So this is equal to I square R. So we know the current I and also we know the resistance.
Teacher,
Yes.
can you repeat this part again?
This part,
Yeah.
they have asked what is the rate of heat produced in this circuit. We know that the heat produced is given by Joule's law. H is equal to I square RT. Rate of heat produced means heat produced per unit time. Okay, so heat per time or energy per time or energy divided by time is power. Heat by time. Okay, so I square RT by time. I square R. Is it clear, Irfan?
Yes, teacher, I understood now.
Okay, now you have to take I square and R. So when you take R, see here you have this resistance R in the external circuit. Plus there is an internal resistance small r, right? You have
Yes.
an internal resistance small r. So here you have to take this into consideration. What is the current I we have? Oh, through the external circuit. They have asked, what is the question? Rate of in the external resistance. So through capital R, how much will be the heat produced? So we can use capital R, and I we have already derived, found out 0.95. So power is equal to, this is for case when we are not connecting AB parallel to CD, only this one. So case 1, so I am writing H1 is equal to I square R, that is equal to 0.95 the whole square times R is 10. So what is the value here? 0.95 the whole square times 10. You will get it as
9.025.
0.025 watts. So this is the power when AB is not connected parallel to it. Second case, we have to consider when this cell AB is connected parallel. We already have a cell here, and at CD, we are connecting a new cell of the same EMF and internal resistance. So this is the second case. Okay, we are connecting that cell AB parallel to CD. So here the cell AB is connected parallel to CD. Now what will be the total power? Power is equal to I square R itself. R is same, but current I will change, right? When two cells are connected in parallel, what will be the current? Is it the same equation? No. This is for one cell. If two cells are connected, what will be the equation? I is equal to, when two cells are connected in parallel. Yes? I can't hear. Are you telling?
Teacher, we have to multiply it by 2.
There was a formula when cells are connected in parallel, I is equal to ME divided by MR plus small r. Do you remember this formula? When the cells are connected in parallel. If they are connected in series, that small m in the denominator will not be with capital R, it will be with small r. That is the difference. So here there are two cells, m is equal to 2. So can you tell me?
Teacher,
Yes.
the EMF of the circuits are same, right? E is equal to 10 volt, then R is
Yeah.
equal to 0.5
EMF
volt.
are
Then
same. Yes.
then we can multiply by 2, right? If we find one current and if we multiply by 2.
No. How can we multiply that directly by 2? We have
Because
derived this
there is
equation. We learned that
the values.
two cells are connected in parallel, their effective EMF will be same as that of one cell. And if two cells are connected in series, their EMF will be multiplied by 2. We are now talking not about the EMF. I am talking about the current in the circuit if two cells are connected in parallel. And we derive this formula for that. So please revise connection of cells in parallel and series. Combination of cells in parallel and series. There we have derived two formulas for current. One when they are connected in parallel, I is equal to ME by MR plus small r. And if they are connected in series, I is equal to ME by R plus NR. We are not talking about EMF, we are talking about current. So here M is 2, two cells are connected. So 2 times, what is the value of E? 10. 2 into 10 divided by 2 into, what is the external resistance? 10 plus the internal resistance is 0.5. So you have to use this formula and solve. What is the answer for current?
0.98.
How much?
0.98.
0.98 ampere. Now you can use this current in this equation to get the second case, how much power is given out. So per unit, okay, so here I am using 0.98, the whole square times 10. What is the value?
9.604. 9.604.
9.604 watts. So in which case 1 or case 2, the power per unit rate, rate of energy dissipated is more. Which is more? First case or second?
The second case.
Second case it is more. So when you connect this cell AB parallel to this CD, what happens? More energy is dissipated per second, or the rate of heat produced will be more in the external resistance.
Teacher,
Yes.
if we connect the battery in the series, then The same answer will come.
No, it won't be the same answer. Okay, let me calculate with a series connection.
Yes.
Here and I will tell if it is connected in series. So let us consider for as a third case, you will have the resistance R here and two cells are connected in series, each having EMF 10 and internal resistance 0.5 ohm. So the current produced in this case, I will be equal to N, using the same terms as we derived. NE divided by R plus small n into R. Okay, so N is 2 here. 2 times 10 divided by 10 plus 2 times 0.5. Calculate and tell me this value. You can use the calculator. 20 divided by 12.05. How much is 20 divided by 12.05? Is 12.5.
Teacher, it's 1.659.
1.6.
1.659 approximate.
1.65 amperes. Okay. So what will be the power? 1.65 the whole square into 10.
Teacher, it is 27.54 by what?
27.54. So when the heat generated will be maximum out of all these three cases when the cells
Number
are
3.
connected in series.
Series.
Okay? When the
Teacher, we
cells,
will get more power also, right?
yes,
If we connect them in series. It's beneficial, right? If we connect them in series.
if it
Because
is,
we'll get more power.
it depends upon our use. If you want to generate more heat, suppose if you are using something as an iron box, then it is beneficial. See how much high the heat produced is. Then it is beneficial to connect the cells in series. But otherwise, suppose this is a bulb. Okay. Then also the energy is produced, converted into heat. Then also this is beneficial. But if you have a fan, motor fan, as this external resistance, then is it beneficial? No. Because what happens? More energy is lost as heat. We don't want the energy to be lost as heat. So it depends upon the purpose. If you are using this circuit instead of R, you are having an iron box here, then it is beneficial to connect more and more cells. But if you want there instead of an iron box something else like a fan or something other than that, where you don't want to produce heat energy, then it is not beneficial.
Yes, teacher. Understood.
Is it clear, Irfan?
Yes, teacher, it's fully clear.
Yeah. So it depends upon what R is. So let us go to the last problem, that is 340. Question number 340. Ronnie, can you read question number 340? Is Ronnie there? I think he left. Okay, Hasina, can you read question number 340, which is in page number 207?
Okay. Find the equivalent resistance of the circuit A, and then B is to get same amount current through R3 as that of R1. How much resistance in which way is to be connected with R3? Give your opinion with mathematical analysis.
Okay. So they have given a circuit, right? So there is a circuit. And they have given 3 resistances here. 6 volt, R1 is equal to 3 ohm and R2 is equal to 6 ohm and R3 is equal to 10 ohm. Okay, this is the connection. Find the equivalent resistance of the circuit. That is easy, right? Just you have to find these two are in parallel. So we have 1 by Rp is equal to 1 by 3 plus 1 by 6. To make the denominator same, this is equal to 2 plus 1 is 3 by 6 or is equal to 1 by 2. So Rp is equal to 2 ohms. These two in parallel. So the effective resistance is 2 ohm. And they are connected in series with R3. So R effective will be equal to Rp plus R3, which is equal to 2 plus 10, that is equal to 12.
12 ohm.
So this is easy. What is the equivalent resistance? Now next question is to get same amount current through R3 as that of R1, how much resistance in which way is to be connected with R3? Give your opinion with mathematical analysis. So we have to find how much is the current going through R1. Let me name it as I1 and this as I2. Here the same current I will split into I1, I2, join up here and I will come, right? So the question is, what resistance should be added to R3 and how it should be connected so that the same current I1 will flow through R3. So let us first find out what will be I1. So how will we find what will be I1? You have the potential, first of all, you have the main current, right? You have the main current, I. So first,
So we can use Kirchhoff's equation
what?
here. We can use the equation, Kirchhoff's equation, I think.
Kirchhoff's equation here. You are telling?
Yeah. Yes.
Yeah. But before that, we need to know the current, right? We know the effective resistance and also the potential is given. Pole resistance, we know. Pole current, we know. So directly we have current I is equal to V by R, R effective for the whole.
Teacher, the class will be end in 1 minute. Less
Okay.
than 1 minute left.
Okay, let us try to finish off fast. If you tell me the value 6 by 12, that is equal to 1 by 0.5 ampere. Okay, that is the current, whole current. Now we want to find what is I1 and I2, right? And also,
Yes.
so how much will be the potential dropped across this? The rest, 6 volt is there. 6 volt, some